All right, and so now we've reached the final portion of our understanding of an action potential, in which we basically answer the question, why do we have them? Who cares? What does an action potential do? Etc., etc. So just to quickly review, action potentials are a massive and very quick depolarization in the membrane that results from reaching a certain electrical threshold. So what happens is we have a threshold that we'll say is right up here. You have graded potentials add up, add up, add up. They hit threshold, voltage-gated sodium channels open, massive depolarization. They close, but voltage-gated potassium channels open, massive hyperpolarization, a little bit of an overshoot because potassium's open for a little bit longer, just owing to the kinetics of the channels, and then we return back to baseline. So just looking at the structure of this, you can see what a dramatic figure this action potential cuts. It causes a change in voltage that's much larger than the actual sum total of the graded potentials. Jumps it up to positive 30 millivolts. I mean, if you think about it, if you're going up to negative 50 or even negative 40, well, that would be a change from 65 of between 15 to 25, and then it jumps up about 55 millivolts over the course of the action potential. So this is a very substantial thing that happens in the neuron. So why do we have them? What's the purpose? Well, these action potentials are designed to be increases in the voltage of the membrane that are so big that they cannot be ignored. And the reason this is important is because they trigger a chain reaction where this huge depolarization will then activate another series of voltage-gated sodium channels that will itself have its own huge depolarization. That'll activate its own voltage-gated sodium channels. Depolarization, activation, depolarization, depolarization, so on and so forth. So this is so big because the purpose of this is to move a signal forward by creating such a dramatic increase that it actually causes a depolarization in the next part of the membrane. It actually will trigger another action potential in the next part of the membrane. So the action potential is more powerful than all of those graded potentials that had to sum in order to initiate the action potential. That action potential will have enough power contained within that depolarization to start another action potential all unto itself. So the action potential serves as a mechanism of getting a signal from one end of the cell of the neuron to the other. So again, here we have neuron, dendrites. All of these dendrites have their own little receptors. They communicate electrical activity to the axon hillock. Axon hillock says, okay, action potential time. And here we have an axon. And that axon terminates at an axon terminal. And within that axon terminal are all of the little vesicles in here that contain neurotransmitters, NTs. So, why have an action potential? Why not just have graded potentials that can just flow everywhere? Well, for one, graded potentials are totally wimpy, and they can't make it all the way down to the axon. They wouldn't be able to make it all the way through this huge axon. A lot of them can barely make it to the axon hillock. And they're definitely not at full strength because graded potentials, just little electrical potentials, electricity will just diffuse in all directions. That electrical current will it'll go everywhere and it'll become smaller and smaller and smaller. Um, it'll degrade over space. So it's the activity of many, 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 many different excitatory electrical signals that have even degraded by the time they get to the axon hillock that'll start the action potential. But as we mentioned, the action potential isn't wimpy like a graded potential. it is a huge depolarization, and it's so big that it causes another depolarization, it causes another action potential right next to it. So it goes on and on and on. So what happens is the action potential fires, action potential, action potential, action potential, action potential, action potential. It'll just propagate through a chain reaction. It'll cause action potentials that'll just go up the entire axon, and eventually they'll hit the axon terminal. Now those voltage gated channels that we talked about before, they're not just, throughout the axon. They have to be throughout the axon. Otherwise, how is it going to conduct the action potential? So they're all throughout the axon, but there are other types of voltage gated channels in the presynaptic membrane, specifically voltage gated calcium channels. And when calcium flows into a cell, that is when all manner of fascinating things happen. So what happens with the voltage-gated calcium channels is they detect that an action potential has propagated all the way down this membrane. And it will have a conformational change responding to the depolarization of the membrane, because, hello, it's an action potential. That's what they do. They depolarize the membrane. That'll allow calcium to flow into the cell, and that'll cause neurotransmitter release. So the action potential is a unique electrical signal that is so big that it stimulates another electrical signal right next to it, and then that's so big that it stimulates another electrical signal. It's a huge electrical signal that causes a chain reaction down the axon, which will then allow for calcium to flow into, it'll then affect receptors on the other side of the axon, because it's propagated all the way down here. It'll affect receptors down here that allow ions to flow into the membrane and cause the release of neurotransmitters. And then those neurotransmitters will go and they'll communicate with another axon, or it'll communicate with dendrites of another neuron, and then that will tally them up, fire its own action potential, that'll propagate down, and so on and so forth. And that's how neurons talk to each other. But you can see that you could not use a graded potential here, because let's just say that the neuron we have a hypothetical neuron with an axon. If we had graded potentials, they would all fizzle out way before they could get down the axon. Even if they were originating from here, they wouldn't be able to travel down because they degrade, and there wouldn't be any propagation of an electrical signal down the axon. So all of these graded potentials serve one purpose, and that is to fire the gunshot and start the chain reaction. That is the action potential. That'll go down, hits the terminal, activates receptors, and that causes the release of neurotransmitters. So that's why we have action potentials. They're big, they are stereotyped, they have a common shape, because they're not graded, they don't change in size and they don't change in magnitude according to input. They just fire. And again, they'll fire more frequently as the intensity of a stimulus increases, and what that'll cause is it'll cause more release of neurotransmitters. The more frequent the action potentials, the more calcium, the more neurotransmitters you have. Simple enough. So, basically, now that we understand what an action potential does, that it is a potential which causes a chain reaction and has the capacity to initiate action at the axon terminal, action in this case being neurotransmitter release, then we can start to talk about more effective ways to conduct the action potential. So what I just described to you, neuron, dendrites, axon, terminal, that's a pretty simplistic way of thinking about it. Action potential will just go down here like this, and then propagate down each time it is exciting the membrane next to it. This raises one question initially, and that is, well, why does the action potential just travel this way? Why doesn't it travel this way? It is electrical, it should diffuse evenly across space, so why is the action potential always moving in one direction? Well, let's take a look here. Here's our action potential. So remember what happens here is there is opening of voltage-gated sodium channels. And here, they turn off. The voltage-gated sodium channels will shut down. They will inactivate. They cannot be opened again. And what that leads to is during this phase here, where all the potassium is flowing outside of the cell and it's becoming hyperpolarized again, you cannot have another action potential, no matter how hard you try, because those sodium channels are inactivated during this entire falling phase. And you need sodium channels activated in order to start an action potential. They're inactivated, they're shut down, they can't open. This is what we call the absolute refractory period. It is absolutely impossible to start another action potential during this absolute refractory period. There's another refractory period that remember, eventually these channels are going to open back up. So once they open up again, you can fire another action potential if you'd like. But there is a brief hyperpolarization of the neuron's membrane below resting membrane potential from all of the potassium being allowed to do what it wants, which is make the cell much more negative. And this is called the relative refractory period. And so when the sodium channels are closed and they cannot open up again, that's the absolute refractory period. And when the sodium channels are open, but the cell is a little bit more negative than it would be otherwise, that's the relative refractory period. And we just call it the relative refractory period because, yes, the cell can fire, the neuron can fire another action potential. It's just a little bit harder because instead of going from the resting membrane potential, it's going from a slightly hyperpolarized membrane potential here. So the reason that the action potential only propagates in one way is because of these refractory periods, specifically because of the absolute refractory period. So when an action potential fires, just in theory, if you have a membrane here and you have an action potential that fires, it can go one of two ways. It can go this way or it can go this way. Well, it isn't going this way. Or when it goes this way, it's not going to have any effect because all of these voltage-gated sodium channels are shut. They're closed. You cannot have another action potential this way. The only way that you can go, or the only way that you're actually going to get a response, is from the signal traveling this way, because these channels are open. Now these channels have closed, so this action potential, it can go this way and this way, but it's only going to get a response going forward because now these channels are closed. It goes up, these channels are closed, it can only go this way. These channels are closed, it only goes this way, so on and so forth. If you think about it, those cartoons where they have, a little fuse and then there's a bomb at the end of it, and, Wile E. Coyote or whatever lights the fuse and then it will go, and then it will eventually explode. The reason that action potentials only propagate in one way is the same reason that the fuse only moves in one direction, is that this fuse here becomes burned out. So that can no longer catch on fire once it's been burned out. So the fire will only travel one direction because all of this rope here has been effectively inactivated. It's the same thing as having sodium channels closed. Now, it doesn't disappear, but it's not going to catch fire. So the same principle that dictates that a fire will travel in one direction up a rope holds when you talk about the propagation of an action potential. As the action potential continues to move forward down the axon, the reason it moves in one direction is because this area back here becomes, after an action potential fires for a brief period of time, that area is closed and it cannot take another action potential. So again, membrane, action potential, this area is closed. Positive charge moves forward, another action potential. Now this area is closed. Positive charge moves forward, action potential. This area is closed. So on and so forth. So it only moves forward because that's the only place it can move. And the movement of the action potential in one direction towards the axon terminal is because of the refractory periods during which those channels are closed. So, in the hypothetical model that we had, this will be the last thing we talk about. You have your cell body with your dendrites, and you just have your axon, terminal, action potential moving down like so. Well, what would be a more efficient way to move this action potential down the axon is not actually by just having a chain reaction, which moves it down one step at a time, but instead to have little bases where you fire an action potential here, then you fire one here, then you fire one here. So instead of 100 action potentials to get from point A to point B, you could have 2 or 3 at most. And the way this is accomplished is by myelination of the axon. So there's just a fatty insulating substance that's wrapped around the axon called myelin, and it increases the resistance of the membrane. It increases the external resistance, I should say, by so much that the charge moves very quickly down an axon that's been insulated with myelin. I'm not going to get into the physics of this, but suffice it to say, it's like uh, if you had a leaky hose and you wrapped it up with tape or with duct tape, you'd have an increase in water flowing out the front of the hose if you wrapped it up because you're making it so difficult for the water to flow out of the leaky spots that more of it ends up at the other end. The same principle holds with myelination. You increase the external resistance, and then a charge, even a wimpy graded potential, is going to move in. It's going to move in one direction. It's going to move it there very quickly. So what happens with myelination is you have an action potential, fire, 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 and then you have a charge at the end of that action potential, and at this point you're just a graded potential. You're just like any other lame graded potential, which is weak and isn't an action potential, which is awesome, and that graded potential will deteriorate over time. But the thing is, with myelination, the graded potential moves so fast down this axon, it doesn't really have too much time to degrade. And when it gets to another node here, call these nodes of Ranvier, when it gets to another node here, it's still at threshold and it can still instigate some more action potentials. Then it turns into another wimpy graded potential. It'll deteriorate over time, but it's still once again at threshold here, so you can fire some more action potentials. And what this basically does is it causes an action potential to leap from here to here to here, and we call this saltatory conduction. It's an O. Saltatory, I believe, is from, I think it's Greek. It means to leap. And so what this does is it's a much more efficient mechanism of moving an action potential down an axon. So instead of just going across the whole thing, it goes boing, boing, boing until it eventually hits the axon terminal, and it causes the same response. So when you're dealing with principles of axons, as we'll see perhaps later in the course, and certainly in any neurophysiology classes you're going to take, there's a lot of different things you can do to an axon to make it conduct an action potential more efficiently. But one of these is to increase myelination, because it makes it much less, it increases the conduction of the electrical potential down the axon. And I'm really probably just confusing you. It's not really pertinent to understanding the action potential. But suffice it to say, myelination makes these graded potentials move much quicker. Making the axon bigger also makes those action potentials move much quicker because that decreases internal resistance. I know I have some engineers in the class, so that will probably help them out. But the point is that this form of jumping from node to node to node is a more efficient mechanism of conveying the signal of the action potential down the axon. And in some diseases, such as multiple sclerosis, you actually have the myelination deteriorate so that the signal will travel in that old-fashioned way, and it will make it a little bit more difficult to initiate actions or things like that. So now you all know the chemical and electrical properties behind the action potential, the electrostatic and the diffusion forces, how those contribute to the equilibrium potential. You know the different stages of the action potential in every single one of these little depolarizations here. And then in addition to all that, you also know the general function, what it does, how it moves down the axon, and what it causes at the end, which is release of neurotransmitters. So I hope that this has been useful. I hope that it makes the entire thing a lot more simple to understand when you're literally just dealing with ions trying to get to their various equilibrium potentials. I know that's the only way that I could learn it. And if you have any questions about any of this or you want me to explain another thing, please feel free to send me an email um, and just put in the subject line like a YouTube video where I'd like an explanation. And I'd be happy, or even I could explain it in class, I'd be more than happy to talk to you all more about this. It's pretty important because action potentials are the way that neurons communicate with one another. So if you are going to take any other classes in neuroscience, you have to understand how action potentials work. But um, but yeah, as you can see, it's made up of a lot of different steps, but it's not that complicated. It's just a gunshot that causes a chain reaction down an axon and will eventually release neurotransmitters. That's it. So I hope you have found these once again useful, and just give me a ring.